Hi, this is Richard Lenz with RealAcoustix. I'm here to talk to you about how to read a GLL file. As many may know, there is a new ASTM proposed standard for diffusion and how to read and understand what a diffuser and or a scatterer is doing. And that is, in order to be able to do that, you have to have the ability to read what is called a GLL file. A GLL file is a file from AFMG, the great makers of Ease and Ezra and many other programs. And it is originally designed, this was from a program called Speaker Lab, for assessing the performance of speakers. We have basically taken, Ron Soro and I, about 12 years ago, decided that the two ISO standards, ISO 17497-1 and -2, were insufficient to really understand what a diffuser is doing and is it truly diffuse, and or scatterers and what they look like and what their performance looks like. So what we've done is we've taken the AAS 56, and instead of a direct reading, we are using a first reflection. We'll go into that in another detail in another video at some point in time. But this one is basically so that you can understand how to read the GLL files that we and many other manufacturers provide in order to be able to assess the performance of a diffuser. So the first thing we want to take a look at is how to download the GLL file. So I'm going to share this with you. The first thing you want to do is get on the website. And basically all you do is go to AFMG/GLL, just type in AFMG GLL, it'll research it. You can click on the GLL Viewer tab, and this will take you to this window here. There is the download. It's a free download. There's no cost to it for the GLL Viewer. And then if you don't have, and most likely don't have, Microsoft Net 3.5 framework on your computer, you will want to download that as well as it is necessary in order to read the file. So at that point, once you have downloaded this, you will end up with an icon that says Ease on it, and it's very easy to see that, and it's a big red icon. You double click on that, or in most cases, what you'll end up doing, and I'll share again, you're going to end up going to our files, which will open up, and this is what you will see. When you first open up the AFMG GLL file, the first thing that'll pop up is a representation of the device that you're looking at, whether it's a diffuser, a scatterer, or any other product, similar product. It gives you this rather drafted look of a diffuser. In order to really start understanding what the diffuser is doing, we have to go first into Calculate, and then we'll click on Balloon. Now, these settings in the calculation parameters are very important to note. The temperature or the resolution, 10 degrees is just fine. That's 6. This distance in meters. So what this is doing, important speakers, yes, you may want to take a look at a speaker in a concert hall at 100 meters, but in this particular case, we're looking at a diffuser. We want to look at it probably at 5 meters is the most standard. You could look at it for up to 10, but 5 meters is a better part of 16.5 feet. And that's generally sufficient for most applications. So aside from adjusting the distance, you also want to disable the enable air attenuation, because we don't want air attenuation in there. And then you also want to click on the AES2 broadband pink noise. That's important because that's how the test was conducted. So once you have done those settings, click OK. And the first thing that'll pop up is this. This is a balloon. So for those of you not familiar with the concept, a balloon is basically a 360, or in this case, 180 degree module that shows how the reflective performance of the device is working. We will want to make a couple of changes here. First thing, we want to go down to third octave analysis, not 1/24. That's a little high res for this application. we'll want to start off at low frequencies. So this particular device is a one-dimensional QRD, quadratic residue diffuser. And in our case, all of our 1Ds are named by the number, the Schroeder number, the design frequency of the quarter wave. So in this case, this is an RQS 450, so it's a 450 hertz design. And we want to take a look at it, and it's important to show you the difference between understanding what diffusion looks like and what a specular reflection looks like. So we go down and let's click 200 hertz. And what you see here in this big round circle is essentially a specular reflection. The specular reflection is one that is basically bouncing off of it because of the pressures in the cells of this device. It's just bouncing off. It's not performing anything. It's just these frequencies don't have any efficacy in the diffuser itself. So they're just bouncing off. It's a specular reflection. For those of you who don't know what the concept of specular means. But so if we go up to 400 hertz, we start to see a little performance on the outside of it, but it's still a large specular reflection in the center here. And that's typical because even though the quarter wave design frequency is 450 hertz, in truth, a quadratic with its Schroeder design frequency is going to be at least a half to a full octave above the design frequency, if not more, depending on what it is. So in this case, we're going to go up to 500 hertz, and you still see that it's specular there. And this is indicative of what it does. This is what we've not been able to see in other tests as to how they perform. 630 hertz, you can see it still has a lot of specular nature to it. We get up to 800, now we're starting to see some performance in the diffuse range. As the specular range becomes much smaller, we start to see breakup here. And that breakup reflects diffusion and diffusive performance. It's not incredible at this point, but now we start to see real diffusive performance when we get to about 1,000 hertz. And this, again, is to be expected because of the nature of the design and the quarter wave. So as we look at this, and we're looking at a 3D perspective right now, you can change the views at any point. You can go to a side view. All of these are helpful to understand, especially in one-dimensional versus two-dimensional, how the diffuser is performing. We can go to an end view, which is basically facing you. And what we see here in these views, and then the plan view is a top view. What we see in these views is how, in this particular case especially, a one-dimensional is working. One-dimensional diffusers have strictly horizontal performance. I shouldn't say strictly, but for the most part, their main efficacy is in the horizontal plane, and there's very little energy that is spread to in the vertical plane, either up or down. And that's important to note because as we start to look at these and what you want to use your diffuser for and where you want to use it, this becomes very important. We really start to see this come in at 1250 hertz. Now, all of a sudden, as we take a look at these different views, especially if you take a look at the side view, you can see there's hardly any vertical dispersion whatsoever, but there is a tremendous amount of, when you take a look at the end view, you can see that it is all coming out in the horizontal plane where all of its efficacy is. So as we take a look at all of these things, we can say, okay, now I see where this is diffuse, and we can again go up in the frequencies, and you can simply click the up button to go 1/3 octave at a time and see what its performance is. And you'll see it's narrower in some frequencies. This is very typical of diffusers. As we start to go up in performance, we will start to see it narrower. So this is where we start to determine how efficient the unit is and at what frequency it starts to taper off in efficiencies. So you can see by the time we hit 5K, it is down to almost nothing. Now, there will be other frequencies where it spreads out a little bit more, but this would be typical of the performance of the RQS 450. So starting somewhere around 1250 to 1500 hertz, it becomes very effective. And at about 5K, it's lost most of its efficiency. It's not that it still isn't performing. Again, we can see 63, 8K. If you're directly in line with it, as you would be, for instance, in a studio application, it will still have efficiencies in these upper ranges, but you'd have to be sitting in that spot to understand that. So as we look at this is kind of gives you an indication of what is really going on. Where it becomes very interesting to understand what the difference between diffusion and scattering. So we go back down into these ranges. I'm going to go back down to the 630 where we have strictly a specular reflection. I'm going to change the graph. In this case, I'm going to look at a phase balloon. So when we look at phase balloons, and you can see here these big, what we call flowers in a sense, with this type of look, this is specular reflections, and you can tell what a specular reflection looks like. When we start to get up in the performance range, all of a sudden those larger leaves, as it were, become much less specular and much more into the diffuse range. We can start to see the breakup here in the phase. This is changes in phase. Now, there is a way to look at this numerically as well, but unless you're really into the science of it, it's probably not. It's probably more important just to be able to understand that this breakup that we're seeing, the more it breaks up, the more diffuse it is. And that's very important to understand how a diffuser works and what it's doing, and how it's performing, both in the balloon as well as what it's outputting back to the listening position. Diffuse reflections we'll go into another video as to what a diffuse reflection is and what they're doing, and how a diffuser differentiates from a scatterer. But this is important to note that we've never been able to see this until now, as to how a diffuser performs in that range. One of the other things we want to take a look at, and we'll go back down to, let's say, 1250. We want to take a look at there is a way to look at the total performance. So in the horizontal map, which, we have both horizontal and vertical maps, we can actually see the whole spectrum of performance of the diffuser in this horizontal map. As you can see, it kicks in as we saw, somewhere around 400 hertz. You can see where it starts to kick in, and it's diffusive performance all the way up here. And you can see where the diffusion narrows, but it's still performing all the way up to even 16K. But again, that's a very narrow plane. This is really its operational range, what we consider its operational range, which would be somewhere between about 1250 and 4K. But again, there's still going to be operational range, just much more directional when you get up there. You can do the same thing looking at the vertical plane. And with a 1D, this is especially obvious that there is very little vertical dispersion at all, and it's nuclear small there. But it is one of those things that we get to see a lot of different types of things. There are a lot of different things that you can look at, a lot of different ways to look at these. Some of them are really more pertinent to speakers, but in this particular case, you can really analyze and start to see what the performance of a diffuser is much more carefully than we've ever been able to see it before. And that's one of the things that one of the reasons we created this test was to be able to really analyze. There are going to be those acousticians and people that say, I missed that single graph. It really told me a lot. No, it didn't. It didn't tell you much of anything, to be honest with you. Now you can really see on a frequency basis what diffusion is, what diffusion isn't, what scattering is, and all of that. I appreciate the time and the ability to present this to you. Hope that you understand that we're trying to improve the acoustics industry and the way that we look at materials and how they perform.